Swayam Prabha. Digital India. Educated India.
Okay, so welcome to lecture number 29 of the Statistical Thermodynamics for Engineers. So we are going to now do the perturbation analysis of the Schrodinger's wave equation. So let us begin with the time-dependent Schrodinger wave equation. Which is basically H, the Hamiltonian chi by dt. Okay, now we consider two rotational vibrational or electronic states. Okay, so we find that the solution to this particular equation, say if this is 1, the solution to this particular equation is given by, we already did this earlier if you recall. So equation 5.38 in the book. So T go to psi r exponential I divided by. So that was the, now for each one of the state, for each state, so let's take the state psi 1. So this is the total psi and this is the R dependent psi. Show minus I silent 1 by H bar psi 2. This is once again the R dependent psi, the exponential minus I energy to T by H bar, where E1 and E2 represent particle energies for the lower upper levels. Respectively. All right. Now, here comes a key piece of assumption. So assuming that any spectral transition is, so we assume what? Any spectral transition is inherently a weak temporal process. Okay, any spectral transition is inherently a weak temporal process. So understand the word weak temporal process. Okay, so therefore what we do based on this assumption is that we can define okay, the time-dependent portion of the Hamiltonian operator H hat prime as a small perturbation. The key word here is small perturbation about its steady state manifestation, about its steady state, okay, which can be written as H naught hat. So it is essentially like your fluid mechanics, the linear stability type analysis, that there is a perturbation component which is time dependent, and it is acting on the steady state manifestation, which is H naught. Right? Okay, so that means H bar is equal to H naught plus H prime. Okay, so that is the total solution. Right? So this is the steady state. All right, and this is the corresponding time dependent. Right. Okay, so the stationary solutions. So the stationary solutions obey okay, H naught n is equal to I H bar dt. Okay. So this is the same strategy. This is the strategy that is used when implementing our time dependent. This strategy is the essential tactic. Okay, this strategy is used for implementing the time dependent perturbation theory. So for our application, the interaction energy, so what happens for our application? That interaction happens between there is an electromagnetic field and the atom of the molecule. So there is, so if we write it, there is interaction between the perturbing, there is a EM field, okay, with atom / molecule, right? Okay. Now that's interaction energy between this, the interaction energy, okay, between the perturbing EM field, electromagnetic field, okay, and atom or / molecule, okay, arises through its electric dipole moment. Nu. So in other words, nu will be equal to summation on Qi. Okay, so Qi, what does Qi actually means? Qi represents the charge. Represents charge. Okay, and what is Ri? Ri represents the location. The location for each proton or electron. Okay, so Ri is a location. It's basically the charge and the location. Okay, so that is what is being summed over all charges and all locations, right? So if you assume a uniform, electric field, electric field E. Okay, we can express the Hamiltonian, the perturbed Hamiltonian, or the time-dependent portion of the Hamiltonian operators H prime equal to minus mu dot E. Yeah, so this is once again the time-dependent portion. Hamiltonian operator. Portion of the Hamiltonian operator. Hamiltonian. All right. So if we take that both the dipole moment, for simplicity, take both the dipole moment and oscillating electric field and oscillating electric field, okay, to be in the same direction. Okay. So in other words, bar mu naught cos omega t. So that means the dot product now becomes the cos. It's a dot product, right? So this was the dot product. So that both the vectors are basically in the same direction. Okay. So this is the cos omega t, where the radial frequency, okay, so the radial frequency is written as omega equal to E2 minus E1 divided by H bar. Remember that E2 is higher energy level, greater than E1. Okay, so the radial frequency of the incoming radiation corresponds to the spectral transition for a two-level system required. Okay, so the radial frequency of the incoming radiation, in this case the imposed electromagnetic field or the imposed electric field, the incoming radiation corresponds to the spectral transition. So the spectral transition of a two-level system. Transition of a two-level system. Right. Okay. So that is what it is. As required, if we have to investigate what is the transition probability, right? So remember, so the transition probability is what we are after, right? So if we now want to investigate this two-level system as a dynamic perturbation about its stationary solution, so what we are supposed to investigate, the temporal behavior of this two-level system. We have so psi t is equal to a1t psi 1t plus a2t psi 2t. Okay, so now what happens? Now that we have done this, now you substitute this into the equation that we wrote just a few minutes ago. What is this? To substitute this into your total solution like this, something like that. Okay, and we invoke equation and we invoke Okay. A1, A1, 28. Okay. So all the terms involving, okay, all terms involving have been eliminated. Okay. So now what happens is that we multiply this equation. We multiply this equation. Multiply, okay, by chi2 star exponential I into t h bar. Okay, so now then we substitute from equations from the by-part solutions that we have already got. That is chi1 and chi2. Chi1 and chi2. So therefore, this gives, okay, a1 e minus I 2 t h bar chi2 star a1 plus a2 star. Okay, so these are once again the R portion, the Schrodinger wave function. Chi2 equal to h a1 bar a1 dot e minus I e2 t h bar chi2 star chi plus I h bar into a2 bar chi2 star chi2. All right. So this is what you get. Now you integrate over all spatial coordinates. Now integrate. Remember these chi will all integrate over all spatial coordinates. Spatial coordinates. Okay, and wave functions are orthonormal, and remembering that the wave functions are orthonormal. Normal. Okay, so, and we also know that omega equal to chi2 by chi1 divided by h at h bar. Okay, so what you get is I h bar into a2 bar is equal to a1 e I omega t integral chi2 star bar at chi1 now plus a2 chi2 star okay, so this is what you get. And according to our so this is the total analysis that you get. So according to our perturbation analysis, states 1 and 2 will differ little from their initial populations. Okay, so according to our perturbation analysis, states 1 and 2 will differ little from their initial populations. Their initial populations. So we have A1 is almost equal to 1, A2 almost equal to 0. Okay, so I H bar A2 dot equal to E I omega T chi2 star perturbed Hamiltonian chi1 equal to tau. Right? So this is what you get. Good. So now, if you now substitute, okay, the expression for H at prime, which is equal to minus mu E naught cos omega t, and substitute it here. Okay, substitute it here. Okay, what you get is I H bar dA2 by dt is equal to, and we will write what the expression is, M12 E naught EI omega t cos omega. Okay, and what is M12? Where M12 is equal to chi2 prime mu chi1 tau. So this is called the transition dipole moment. Okay, which in more general case, okay, so we can write it in a more generic when it is Mij, it is basically, okay, I mu j all right. So the two wave functions here basically chi I and chi j are identify the two states participating in any spectral transition. Okay, so in essence, A2 T, okay, represents the extent of participation in in state 2. Okay. Therefore, dA2 by dt, okay, is interpreted as a transition rate from state 1 to state 2. So that is the transition rate. Okay, so this equation, if you look at this particular equation, which is this right? So if you look at this equation, then this equation actually states that transition between two rotational, vibrational, or electronic states is impossible if M12 is 0. So if M12 is equal to 0, then dA2 by dt is also equal to 0. Okay, so that means transition between between two rotational, vibrational, and electronic states. Electronic states is impossible. Impossible. If M12 is equal to 0. Okay, which other way means if the transition dipole moment is 0. So spectral line only emerges, a spectral line only emerges, okay, when its transition dipole moment is non-zero. Okay, it's non-zero. Okay, so generally you will find more intense lines in the spectrum. The more intense lines in the spectrum arises when Mij is high. Okay, so of course, so you need to evaluate the transition dipole moment, but of course this evaluation does not require the determination of all possible transition dipole moment. So mathematical symmetry of any wave function is also used. Okay, and so these rules can be, the selection rules can be expressed in terms of the allowed changes in characteristics quantum numbers. But this is how the situation happens, right? So we can say that the transition dipole moment is the most important thing, right? Which determines which are the allowable transitions. This has to be non-zero for us to have an allowable transition. So next lecture we will see that how the selection rules can be cast in terms of simple changes in the quantum numbers, and by using the properties of the different mathematical functions from which these quantum numbers actually emerged. So that is what we are going to do in the next class. So this is end of basically your lecture 29.